I'm kind of moving on to a different type of information. So we're talking about domain and range now. We haven't really addressed this before now. We have kind of talked about, graphs moving up and down. We've talked about circles that are in different locations. We've even talked about, and this is actually Unit 9, I should say. We've even talked about, transformations, making things wider and smaller, stretching, shrinking, reflecting, all of those things. Well, that changes the values of the graph and the x values and the y values. So now we're actually going to talk about defining that. What does it mean for domain? What does it mean to find the set of all x values? What does it mean to find the set of all y values? Okay, so this is what you need to remember. Your domain is the set of all x values that are defined in the function. They go from left to right on a graph. Your range is the set of all y values, and they go from bottom to top. And some students find it easier for me to say, this is the smallest x value to the largest x value, and the smallest y value to the largest y value. If that helps you, you may want to write that down. Okay. We have talked a lot about polynomial graphs, and most of these polynomial graphs do not have domain restrictions. That means that I can plug in any x number and we're good to go. So for example, like if I had x squared, there's no x's that I can plug in here that would make that undefined. I can plug in -1, I can plug in 1,000 if I wanted to, and I would be able to get an answer. Same thing with like a cubic, if I had something like that, I could still plug in any number on the number line and get an answer. But there are a couple functions that we're going to talk about today that is not the case. These are called domain restricted functions. That means you cannot plug in every single number on a number line and get a value for y. So for these domain restricted functions, we're talking about two in particular. The first one is a radical function. So those are the ones that have the square root with it. The other one is rational, and those are the ones that look like fractions. So you need to remember that rational is the same thing as fraction. Okay? Now let's talk about the radical specifically. I want you to think about numbers that we cannot define in radical format. Or I should say, they are, what are our options for only real numbers? What makes an imaginary number? So remember, we've talked about radicals before, and that if we have a square root of a negative number, whatever that number is, I end up getting out an I. And this is what I'm saying is I can't graph that value on a graph. I want to be able to plug in numbers that I can't. So I need real solutions to this, not imaginary solutions. And I'm getting those imaginary from having negative numbers. So if I can't have negative numbers, that means I can only have positive numbers, because I could find the square root of any positive number, even if that number ends up being like 2 squared of 3. That's still a real number. I can put that in the calculator and find a decimal approximation. But what about 0? Could I find the square root of 0? Yes, that would be 0. So 0 works also. So really what I'm trying to find is any number that is 0 or higher. Because if it goes in the negative direction, we're no good, because we end up in imaginary territory. And that is what this is saying. That these numbers underneath must be greater than or equal to 0 in order for me to have a real number answer. Anything less than that is going to give me an imaginary number. Okay? So this is the setup you need to remember. And I'll say the numbers under the radical, but the name for that is radicand. So if the radicand, you're taking the radicand, just the number under the radical, and setting it greater than or equal to 0 and solving. You should note that the interval notation always includes a bracket. And why is this? It's because of that equal to right there. Okay, so let's look at this first example. We have f of x equals square root of x plus 1. Our radicand here is x plus 1. So if I'm following this format, I'm doing x plus 1 greater than or equal to 0 and solving. So this is minus 1, x is greater than or equal to negative 1. So now I can write this I can graph it and write it in interval notation. And when it's asking for domain, it wants it in interval notation. That's what it wants. It does not want you to write this. It wants the interval notation for this. So let's sketch a quick graph. If this is negative 1, I'm going to the right, and this is going to be a bracket. So interval notation, again, arrow points right, shade to the right, infinity's on the right, and the numbers on the left with a bracket. And that would be your domain. So your domain for this problem is all the numbers negative 1 to infinity. And let's see if that makes sense. If I plug in negative 1 in here, negative 1 plus 1 is 0. Square root of 0 is 0. What if I plug in 0? 0 plus 1 is 1. Square root of 1 is 1. Okay, and I could keep going. So any of these numbers would actually work in this and not give me an imaginary number. All right, so that's radical functions. You need to make sure you know the difference between the setup for radical and rationals. A lot of students mess this up. So keep in mind, this is going to be an interval greater than or equal to 0. This one is different, okay? All right, we've talked about rationals before. You've even graphed these with parent functions. And if you remember, the parent function of a rational looks something like this. And you know that for the x value, when the x value hits 0, it's undefined right through here. The graph never ever actually touches that. Okay, so this is because we cannot have a 0 in the denominator. And y'all know that that's just kind of like the normal rule for fractions. Okay, no 0 in the denominator. Think back to the slope. Remember when we were doing slope of lines and we had a 0 in the denominator? It was undefined. And that's a reason, because you cannot have a 0 in the denominator. Okay, so the setup for this is you set the denominator not equal to 0 and you solve. Our interval notation is going to include this union because we're skipping over some number. We're saying that there's some number there that's going to make that denominator 0. And again, going back, we also talked about this with rational equations when you had all those fractions in the problem and we had to figure out, is this a valid solution? Does this make this 0? Same thing here. Okay, so what I'm trying to find is, what is the x value that makes 2x minus 4 equals 0. And so what we're going to do is say 2x minus 4, we're saying, ooh, this cannot equal 0, because if it does, it's undefined. So let's see what that x value is. So that x value is 2. So let's see if that makes sense. 2 times 2 is 4, 4 minus 4 is 0. So 2 is not a valid answer, as in it's not in the domain of the function. It is not in the domain of the function. It's not, this number is not included in all the available x's. Okay, so if I was to graph this on a number line, this one's a little different. So here's 2. And what I'm saying is that 2 cannot be an answer. So even though I know we've done like parentheses and brackets before, here we are putting an open circle, but we're just doing that because there's a hole in the graph right here. And you can think about this as, you know, if we think about this, there's this place where the graph's not ever going to touch it. So it gets really close to this 2, but it doesn't actually touch it, but it can be every other number. Can be every other number. So how would we define this interval? This would go from negative infinity, all the way up to 2, really close to 2, but not including 2, so no bracket there. And then it's going to skip over 2, so that's union because we're joining these two things together. It's going to start back up the other side of 2 and go on to infinity. This is the format for every one of the rational answers. So the only thing that's going to change in your answer for this domain are these two numbers. Okay, so it's always going to be negative infinity up to something, union something, infinity. Now, there are some more complicated problems where you may be skipping over 2 different numbers on your homework, but in general, this is the format. Okay? All right, let's move on. We're also going to talk about determining if a relation is a function. So we have a relation. A relation is just a relation between two sets is a collection of ordered pairs containing one object from each set. If the object X from the first set and the object Y is from the second set, then the objects are said to be related if the ordered pair XY is in the relation. A function is a special relationship where each input has a single output, which means that X values cannot be duplicated, and that's the key to this. So basically, it's a relationship between the numbers. It's like, hey, 8's going to relate to -9, 1's going to relate to 4, 1's going to relate to 2, 6 to 2, 3 to 2. Okay? And what we're trying to determine in this type of problem is if this relationship that we have drawn here is a function. And it's only a function if each input has a single output. That means this is only paired to one of these. Well, look at this one. This one is paired to this and this. So that's a problem. Okay, X values cannot be duplicated, therefore 8, -9, that's just one value paired with it. But if I was to write this ordered pair, I would have 1, 4, but then I would also have 1, 2. And because 1 is showing up twice, so I've got 2 numbers coming off of that 1, then this is not a function. Now, if this was a function, we may be able to come up with a domain and range. The domain and range would just be the set of all X values, and this first set would be your X's, and the set of all Y values would be your range, and that would be your second set here. Okay? Let's look at this one. I've got 1 paired to 7, 8 paired to 4, 9 to 1, 7 to 3. So none of these X values are repeated, therefore this is a function. And if it is a function, we can list the domain. Now the domain is listed as a set, so we do the little braces, set notation. And we're going to have 1, 8, 9, and 7. And the range is going to be 1, 7, 4, and 3. And you're not going to repeat things in the same set. And we'll see what that looks like over here on this one. Okay? Now, I do want to make a quick point. This did not happen in this one, but in this problem, we had 2 lines coming off the 1, and this was the part that was the issue. But notice that you actually had 3 numbers coming to 2. That does not matter. It does not matter how many numbers are pointing to this Y value when it's talking about function. That will matter later when we talk about one-to-one functions, but when we're just talking about functions, this is irrelevant. So really what we're looking for is 2 numbers coming off any of the X values. All right? When it's listed as ordered pairs, all we need to do is just look at our X values and make sure they're not duplicated. So here we've got 3, 2, 9, and 6. None of those are duplicated. So is this a function? Yes, it is. Our domain is the set of all X's. So we've got 3, 2, 9, and 6. Make sure to use your little braces. And the range is the set of all Y's, and this is what I was talking about. If it shows up more than once, so like here you have a 3 and a 3, you don't have to write 3 and 3 down here. You just write it one time, just one time. So I have 3, 4, and -5. Okay, So that's when we're given like a set or a relationship diagram. All right, looking at the next thing, we're talking about a vertical line test. So if we're given a graph, we can determine if it is a function by drawing a vertical line anywhere on the graph. If that vertical line hits the graph in more than one spot, the graph is not a function. So I want to just draw some examples so you see what I'm talking about. If I had a graph like this, and I drew some vertical lines on it, okay, notice that each one of these vertical lines is only hitting the graph one time. So no matter where I draw that vertical line, it's only hitting it one time, so this is a function. Yes, it's a function. Okay? What about like our standard parabola shape? Is that a function? Let's see. Now we need to keep in mind that this is going up and up and up and up and up, and that this is going up and up. And at the same time of going up, it's also going out slightly. So if I was to draw these lines, it still is only hitting it one time. Even though this looks like it gives the appearance of it hitting more than once, again, remember that this graph is going slightly to the left as it goes. So is this a function? Yes. What about a circle? Is that a function? So if I draw a vertical line, how many times does it hit the graph? It is hitting it 2 times, therefore it is not a function. Okay, and then let's do one more. What about our rational? Okay, so even though it looks really weird, this is actually a function. And this is because it's going to the left slightly, slightly, slightly every single time. So every time I draw it, I'm never going to hit it more than one time. Same thing here. Okay? All right, as you work through your worksheet, you need to remember that your domain from a graph, the domain from the graph is the leftmost x value to the rightmost x value. And your range from a graph is the bottommost x value, or the smallest y value, and topmost, or the biggest, largest, however you want to say it, y value. And you're going to have some examples of that, and I want you to think about going from left to right and going from bottom to top and describing the intervals for the domain and range for those graphs. Thank you for watching. If you have any questions, please let me know.